by this pandemic.
So I have gone into Canvas. I have finally learned more and found time to apply my learned things. And I have tried to organize things a little bit better just in time for the end of the semester. But, you know, at least going forward, I could be a little better at this. You can still access all the old assignments and stuff through assignments. You can still access the pages. You can still access all that shit. It's just your first page when you log into Canvas should look like this now. So at the very top, I've updated the averages as of May 11th. So if you click on that, you should see your grade right over there. This is my test student account. So that's actually the current overall average for the class. Let me see. Is everybody, let me know if you're not with me at some point. So if you log into Canvas, you see this, the overall average is at the top. There's chapter 12 correlation stuff. There's the handouts from that. There's where you turn in homework. And then here's chapter 11 that we're going to get into today. And there's some handouts. Yeah, buddy. A whole new table. That's just too bad. I have no idea. I'm sorry. Statistics is enough torture. I'm not going to add me singing on top of that. I'm sorry. So there's the stuff for chapter 11. I will put homework stuff up there also eventually. Okay. So any questions on that reorganization of Canvas? Just get in there and play around in there. You know, do homework, turn it in, stuff like that. Looks neat. Oh, thank you. Yeah, now, before today was just Band-Aid, do what I can, do what I know. Is it being recorded? Yes. Right? I should be recording. Yeah. Yes, I don't know why you're so, is it being recorded? Yes. Okay, thanks. All right, guys, I'm going to stop sharing. So if you just joined us getting into Canvas, it's been reorganized. And I updated the average for you as of May 11th, as of yesterday. So get in there and take a look. Let me see. Any announcements I want to make? I think I should say, I can't remember if I said this already, but on Thursday, we are going to have a quiz on chapter 12, the correlation stuff. All right. And one step of that quiz will be to take a snapshot of your calculator showing me the line of best fit and all that kind of stuff. So I told you before to let me know if you didn't have a way to do that kind of thing. So I think one person reached out to me since then. So you got to let me know. Otherwise, I don't know how you're going to do that part of the quiz or the final or pass or any of that stuff. Sure. Somebody saying something? No. Okay. So any questions from homework or anything? Okay. All right. So if there's no questions, let's see, when is the final going to be? The same time as it's been since the beginning. So let me see. It's on the homework sheet. It's on the syllabus. I was talking about possibly needing to change the time. I don't think I will now, not for a good reason, but because more people have dropped, which is, I completely understand that this is not the best way to learn this. So several people have dropped. I think we're down to a manageable level. Is everybody aware when the final is now? I mean, if you just look at the homework sheet, the syllabus, it's on both. That time hasn't changed. Everybody with me? All right, Laurel's got it, May 26th. All day long, 24 hours. No, it's, I don't remember where it starts, probably 9:25 or something like that. I'll let you guys figure it out. Or if you don't really know, I could look it up right now for you. Let me see. Do, 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 do. Bow, 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 bow. All right, let's see. Get over here. Where are you at? Math 160 syllabus. Do. So apparently our final, oh, Scheisse. Jeff, you silly boy. It's not on the syllabus because it's different for each of my sections. Let's see. Monday, Wednesday homework. I should have just went to, this is Monday, Wednesday, is it? Yes. Yeah, that's Monday, Wednesday. That's no good. How's everybody doing otherwise? You guys all right out there? Tuesday, there's Tuesday, Thursday homework. All right, here it is. May 26, 9:15. That can't be right. Oh, God, I got to double check that. Jeff, you're silly, Jeff. It might not be 9:15. Let me double check that because it shouldn't be 9:15 to 11:25. I'll double check it. I'll put it up on the canvas, okay? I'll do that. My apologies. All right, but it's around that time on May 26th. I'll put the exact correct time up on canvas so everybody knows. All right. Anything, more people have joined us. So anybody have any questions before I get back into new stuff? Okay, so let me show you something. Let me go ahead and put this back up here. So again, if you just joined us, I've revamped, what do you call it? The Canvas shell. I've revamped it a bit. Oh, good Lord. Reorganized. I reorganized it. What the hell am I drinking? If you come down here, here's the chapter 11 stuff. So if I want to look at this guy, right? Goodness of fit. This is what I'm going to be looking at right now. Let me pull it up over here. Where are you? There you are. Okay. I have no idea if you guys can see that now, so I'm going to start over again. Oh, yeah. Alex has got a good question. Yes. There is a practice final. So I'll be posting the practice final, putting the answer key up. And I think crappity dude. All right, hold on. I'm pretty sure that hold on, everybody. Oh, this is almost too exciting. Let's see. Dude, let me see. You can do it, Jeff. Can you do it, Jeff? Somebody's trying to talk to me. What's up, Alexia? You all right? I guess I didn't put it up here now. Okay, shoot. All right, anyway. So yeah, there will be a practice final. The final is cumulative, like every final is supposed to be, right? Any other questions about that while it's on everybody's brain? There will be a practice final. There will be an answer key for that practice final. The final is cumulative, so it's going to go from chapter 1 to chapter 12. Yeah. It's 2 hours long, as it's supposed to be. All right. It's roughly 100 questions. I'm joking. It's around less than 30 questions total. You know, counting A, B, C, D, E, F, G, H, I, J, K, right? All right. Okay, so not seeing any more questions. Let's get back to this. I just found this. There it is. So here is that handout that's up on Canvas. It's actually called Goodness of Fit. Is there going to be a set time? Okay, all right. Sorry, Chris. Yes, and it's on the homework sheet since the beginning of class. So I'm going to put that back up on Canvas just so everybody's absolutely aware of when the final is and from what time to what time. So yes, okay. So everybody sees this it's got Michigan, Minnesota, all these kind of things, right? Okay. I'm not going to do this right now. I promised my class yesterday I would make a video of this. So you have one more example of this correlation regression, you know, finding the line of best fit, finding R, interpreting those things, right? Graphing it on your calculator. So I'm going to make a video of this. So you have one more example of it in addition to the lecture videos, right? So if you want to try this out before that, so you can compare, or it's just here in case you want another example of the kind of questions I like to ask and the answers that need to happen. Okay. This side 2, is related to what we're going to talk about today. So let me go away from that so it don't freak you out. So let's see. Everybody with me. So this handout is up. It's called Goodness Fit. That's what chapter 11 is. What we're going to focus on in chapter 11 is the goodness of fit, which is an awesome name. But side 1 of this thing is practice for correlation regression for chapter 12. All right, so if you want to do that, you can, and I'll have a video posted, hopefully by later today, of the answers for this handout. Okay. All right, so let me turn off my nifty background. Sorry, spaceman, gets sucked into that black hole. Oh, scheiße. Let me see, is that too much glare happening? A little bit. All right. Go. All right, so what's going to happen, just in case for somehow you forgot how I operate? We're going to discuss the idea behind what we're going to be doing, and then I'll get into some problems that show you the actual nuts and bolts of what you're going to have to worry about. So you're going to have to just absorb what you can from the concept and remind yourself that it's not something you're going to have to do yourself. It's just the idea behind things. So let me ask you this. Let me see if you guys can do better than my other stats class. What governs the shape of a normal curve? I mean, what's the main difference between those two? What governs the shape? Those are both normal curves. What governs the shape of them? Well, you know, pretend like they are. It's not perfectly drawn. What governs the shape? Why are they different? What's different about those two? What governs the shape of those? It is a distribution, but what governs the shape? They are both normal distributions, but they look different. Why? What's different about them? What actually tells me the shape? I love you guys so much. The mean is where the middle, so they could both have the same mean. They could both have a mean of 10. So that doesn't tell me anything. We can do better than this. There it is. I mean, I didn't want to use the word spread. If I would have said what tells me the spread of the distribution, because that's the difference, isn't it? One is more spread out than the other one is. We know that's standard deviation. All right. So you got to really stay with me, because there's going to be a lot of ideas, and I could say them in any order and get them all out there. So you just got to stay with me. So the standard deviation, maybe this one is, you know, maybe they took samples. You guys with me? A little bit? But whatever the standard deviation is, it tells me the shape, like the spread of the normal curve. And what's actually plotted here, what's plotted here, for example, this one would be x values, right? My x value, my variable could be the length of a tadpole's tail. And I plot it, right? And over here, x bar would be what's plotted. Are you guys, everybody with me? Right? All right, this is what we've been doing. This is like me going out of Florida and plotting people's ages. Remember that problem? So one could be individual people's ages, and this one could be groups' means. Okay. In both cases, there is a single value of the standard deviation, right? You guys with me? So maybe this one, this would be apparently when I knew the population standard deviation, but I could also do it where I have a sample and I had to change it, right? Maybe I only know the sample standard deviation. Are you guys semi with me at all? This is all stuff we've done before. I'm just talking about it in some weird ass way. I know, but just stay with me. This is basically what we've been doing up till this point, right? So we're about to make kind of a shift. That's why I like to do chapter 11 last, because it's the one that doesn't quite follow what we've been doing. And the reason it doesn't, the reason we can't expect it to, is because we are going to plot different sample standard deviations instead of plotting different means. So if I take, so this might be created by taking, 40 samples of size 40, right? And this would be the spread of it. This is the single spread of it, and these are the sample means. Plot it out. There's just one spread. So what if instead I took 40 samples of size 40, and I calculated S for each one. For each sample, I calculate S, and then I plot those. Right? You guys semi with me? No? Okay. Well, maybe. So you guys understand what's happening. So everything we've done so far has been about plotting raw variables, right? Just data values, plotting means of those values. We even plotted percentages, and they still follow a normal distribution because we can calculate its standard deviation. And as long as they meet the requirements, n greater than 30, NP, NQ greater than equal to 5, right? As long as they meet those requirements, I know it's going to be normally distributed. Right, it's going to look like a little ghost. Ooh. This guy, I can't expect it to look the same. Because part of the reason this looks the way it does is because of the value of S. It tells me how spread out it is. This is me plotting all the different values of S I get from every sample I take. So the first big thing I'm trying to make a big deal out of is, why can't we just use the normal curve? Well, why would we expect it to look like this if I plot all the individual S's? There's no reason I would expect it to look like this. Did you already mention what exactly S stands for? Oh, okay. What does S stand for, everybody? Yeah, same thing as always stood for, right? Time to take over the world. Sorry, no. S is sample standard deviation, just like X bar is sample mean. They've always meant the same thing. Okay, all right. So one big thing, this distribution we're going to get into, is it can be used to represent spreads of standard deviations. Now that is a very interesting statement, because standard deviation itself is the spread of some data, right? So if I take a group of 40, I calculate its spread, I plot the spread. I take another group of 40, I calculate its spread, I plot the spread, and so forth. Okay. So what shape will this have then? All right, so let's do this. So now we've got the idea that if I plot standard deviations, I shouldn't expect them to have the same shape. So what shape might it have? So let's talk about a candidate, a possible distribution candidate. All right, so, and this is going to be, well, let's talk about it from this perspective. One thing to realize, if I calculate S and I plot it, and I calculate another S and I plot it, what's the smallest that value of S can be? You can do it. What's the smallest that a standard deviation can be? Yes, it can't go negative, of course, right? The smallest it could be is 0. Can somebody give me an example of a list of data, maybe 3 data points, where S is 0? There's an infinite number of answers possible. Just give me 3 data points where S is 0. You can do it. What does S equals 0 mean? There we go. We got 2 right there. The only way to have the spread be 0 is if no data points get away from the mean at all. There's zero spread then. Is you guys with me again? So it seems like this happens in math all the time. Hello, everybody. You learn several things throughout a course. And as you go into different chapters, higher chapters start to take ideas you've dealt with and combine them in different ways. So every individual idea we discussed so far is old news. We've just never discussed it like all at once, and we're going to lead somewhere, right? Now, the one thing that's new is that the spread of standard deviations will have a different shape, right? That's a new idea that we haven't considered yet. Why would we? Now, the smallest it could be is 0. So if I have a population of people and I take 3 people, right? I have the population of America and I randomly pick 3 people. How likely is it that they have the same exact ages? Is it really likely? If you just randomly pick 3 people from all across America and they all are exactly 11 years, 2 months, 3 days, 5 minutes, 2 seconds old. Holy shit, right? That is so desperately unlikely, almost 0%. Well said, Ree. So this should be really low here, and then it's going to grow, and then it's going to shrink. And this actually goes forever because I could have larger and larger and larger spreads theoretically. Just like the normal the normal curve goes theoretically forever in both directions, right? We know it doesn't for like ages and stuff, but still it's a good approximation. But this thing theoretically goes forever. So it makes sense. It's got to have a hard start at 0. And then it grows, and then it's going to shrink because now there should be most of them around sigma, and then a few down here, and then a few get really, really big. All right, let me let you just absorb that for a minute. Now, this is stats 1, technically, elementary stats. There's a lot more that goes into why the shape is that. I'm going to talk a little bit more about another way to see the shape is shaped this way. Is that a sentence that makes sense? And also that explains why the symbol is what it is. Does this make sense though? I mean, you would expect very few up down there, very few that are 0 especially, and then it could get really big. The standard deviation could easily get very big for a sample because you could pick somebody who's 80 and somebody who's 2 and then somebody who's 13 and then somebody's 107. That's going to be a huge standard deviation, right? So it can get really big, but most of them should be right there. I like it. And see how there's no wall on this side, and that's why this tail can get really long. What kind of a distribution is this? Is this a normal distribution? Does anyone know what kind of distribution this is? This is definitely not normal. Do you guys all agree with that? Is it symmetric? Is that how I normally do normal curves? Am I that bad of a drawer? I was kind of hoping I wasn't. It's got a big ass tail over here. This is what I call the Jabba the Hutt distribution. There we go. Laurel's got a better name for it than the Jabba the Hutt, although I still love the Jabba the Hutt distribution. This is definitely skewed right. All right. Okay, maybe. Was it Laurel and Hannah came in with that? I like it. Thank you. Now, I'm hoping to God you guys kind of follow me a little bit as to why intuitively this shape makes sense. The fact that it's down to nothing down there makes sense. The fact that it can go up for a good while because standard deviations could get really big. There's no wall up here really. But then most of them should be somewhere around what I expect it to be. It should be, and to be really honest, I should say to be really honest, I'm kind of plotting the variances. I should actually start with that, but oh well. We're not used to working with the variances as much. Okay, now. And again, remember, We're in the conceptual phase of discussion. This is still not the kind of work you're going to have to do yet, right? Okay. Now, the next thing is, this is so kick-ass. If I take a normal curve, can somebody tell me, somebody have their, let me see. I don't know if you guys can see it. I don't know why I'm writing so small all of a sudden. Can you guys see it? How much area is out there if it was 1.645? How much area is out there? Oh, here we go. All right. Now, wait a minute. What do you mean 0.10? Oh, 0.10 total, right? So 0.05 in both. So yeah, this would be a total of 0.10. It's kind of like could be alpha if we're looking at a hypothesis test or a confidence interval. You guys with me? So I don't have to call it alpha necessarily, but you know, it's the area of the tails. Now watch. Now just stay with me. This is so weird. This is so weirdly beautiful. So these z-scores, right? What if I folded this on itself? What if I folded this on itself? Right? What's 1.645 times 1.645? What's 1.645 squared? And now I'm really freaking you this shit out. What's 1.645 squared? Somebody help me out. All right, to be a little more, go 2.7 what? 2.706. 2.706, yeah? All right, now watch. All right. So it's kind of like if I fold this on itself for higher degrees of freedom, but anyway, if I fold it on itself, it's going to end up looking like this. So I'm saying that if I look up 2.706, there should be 10% above it. That is, if I fold it on itself, this squares. So above this, there should be 10%. Okay, now, just, that's freaky as shit. I know it. I know it is. I know it is. And it's more than you really need to know to be able to do these problems. And that's not the point of a class anyway. If I just show you exactly what you need to do a problem, you don't know shit. All right, so here, let me stop pontificating and let me figure out where the hell I put this. Dadgummit, Jeff. You crazy person. I closed it. Somebody's got a question. Hold on. Here it is. There it is. Okay. Who's got a question? So we can take a two-tail, make it a one-tail. Oh, all right. So there's so much more to this story, and I can't go very much further, which really kind of sucks. It really is dissatisfying for me, but I can't do that because not everybody has enough of a math background to go further. So Raul, this distribution we're going to use is basically kind of built that way. It's built that kind of way. We could do, now here we go. I want to answer Raul's question the best I can without going too crazy. We could do two-tail tests as if it was a one-tail test if I used the distribution that I'm creating, right? Now, all right, that's all I'm going to say. It's some freaky shit. So let me pull up. This is up on Canvas, so you're going to want to get this bad boy. Yes, it is another, it's the last table. So we have Z-score table, T-score table, and now we have these. And these are called chi-square. Can you guys see the chi-square table? Coming at you. Let me see, where's my chat? There it is. Yes, thank you. All right, now, oh, you guys are so pissed off at me right now, I know. It's like, God, what? I finally understand T-scores. All right, you're just going to have to deal with it. It's too bad. One really, really heinous thing about the way this is set up, and it's kind of related to where it kind of comes from. They talk about area to the right. Now look at your z-score table. Isn't the z-score table all about area to the left? You guys with me, right? The z-score table, you're so used to thinking about to the left, below. This one is set up to the right. Now, what did we just figure out right here? If I look up a chi-square of 2.706, and to be honest, this is the part you don't understand, but it's got to be in this first row. It's got to be in this first row. This is like the first row is where things are based off of a normal curve. Once your degrees of freedom starts to grow, it's not quite directly based off a normal curve anymore. But this first row is the one when you fold the curve on itself. So watch, what do you get when you look up, when you find 2.706? What area is to the right? 10%, just like we said. So all right, maybe. Isn't that kind of cool? So if you follow the normal curve and you look above the square of 1.645, if you look above 2.706, it does equal the total 10% that were in the two tails. But you folded it on itself. So now there's 10% in that one tail. Please, somebody let that be cool. No, it's okay if it's not. So do me this favor. Do you see that? I think it's the next one that we can, yeah. What's the square root of 3.841? What's the square root of let me see if that's the one. Yeah. Square root of 3.841. What is that? 1.9. Oh, shit. Alex, do it again. Yeah. If you round it to three places, is 1.96, right? Doesn't that look like a familiar z-score? Hell yeah. Yeah. This one is not on our z-score table. So if you do that one, it won't come out to something we're used to. But if you do this one, 6.635, you take the square root of 6.635, you'll get something that looks very familiar. Anyway, so that first row is directly related to folding the normal curve on itself. There's a whole host of reasons mathematically that is useful. But right now, it's for an elementary stats class. I just want you to have an idea of where this could come from. Okay, now, maybe. So, let me come back to this. Sorry, all right. Let me see. Do I want to? I do. I want to stand up. Okay. Oh, scheisse. Sorry. Now, next step. So, you'll notice there's a method to my madness. I wanted you to understand that it made sense there had to be a new distribution. Then I wanted you to see how it makes sense, some of the values on the chart related to that distribution, right? There's a whole method to this madness. All right. Is it a good method? I hope so. Now, the next thing I want to do is talk about the formulas related to this. So, for example, to bring us back in time, what formulas do we have that are related to this? How could I figure out something that falls on this? What's one formula that's related to this shape? And that's hard for you guys to do. I'm sorry. We know all the formulas. We got to, right? So we got this one, right? And we got this one, right? And then we got the one with an S in there. And then we got this one. I would argue those formulas are in the same form, but are those formulas the same? No. Do they all relate to the same picture, assuming, n greater than 30, np, nq greater than or equal to 5, right? Those kind of things. Don't they all relate to the same picture? They're all scores that fall in this picture and define areas if the requirements are met. You got everybody with me? That's old news. Ooh, Jeff, if I don't know that, I should feel bad because that's what we've been talking about. That's right. Now, what about this shape? the Java distribution, right? You guys semi with me? If you don't like the Java distribution name, I don't care. Now, where did my other pen go? Rawr. There you are. I like this blue pen. So, one equation that relates to this picture. Yeah, right skewed. Alex is like, shut up with your Java. It's called right skewed. It's my Java. Here's what the symbol looks like. Chi-square. That is one symbol. You don't square root it. The square is a part of the symbol. Unfortunately, it has nothing to do with Dragon Ball. All right, so don't get too excited. Right? There's no Kamehameha. Stop. One formula that relates to this looks like this. Does that look familiar so far? No? Okay. Degrees of freedom. Thank you. Now watch. This is kind of neat. This is really, really this is desperately neat. So to make a z-score, I compare I compare the sample mean to the actual mean, right? So here, and I do that through different subtracting, but this one is compare the sample standard deviation to the population standard deviation, but through dividing. It's a different idea, different format of this, but it's still, so it's not the same form, and I shouldn't expect it to be because this is a very different distribution, but it's still comparing the sample standard deviation to the population mean. The same way this is comparing the sample mean to the population mean. Are you guys, is everybody with me? Does that make some kind of sense? So this is very much like a z-score, but it relates to this shape. So all three of these would fall in this shape. This one would fall in this shape. It would actually fall somewhere in this shape. So let's try a problem out. Let's try to use this formula real quick before I go to the formula, the other one. What if I had a problem where n is 40, s is 7.8, and sigma is 8.2? Can you guys all see that? Dadgummit. I love having a cold, and the time of COVID especially. Oh, jeebus. Here, you guys, I'm going to get out of the way in a second. You guys take a second and try to calculate that chi-square. I'm going to go blow my nose. Let me see. Let me do it real quick. Is anybody able to get that yet? I don't even know if you guys can really read that. 7.8. Oh, sorry, guys. You guys figured it out. Okay, let me see. So it'll be n minus 1, so it'll be 39 times s squared, 7.8 squared, divided by 8.2 squared. Holy shit, Jeff. If I could just type. What'd you get? 35, yeah. I get 35.288. Yeah? All right, maybe. Now watch this. So, okay. If I take a good random sample, what do I expect S to be related to sigma? Same question is, if I took a really good random sample, what do I expect X bar to be in relation to mu? What's the best guess for what the S is going to be? You could do this. You could do this. if I take a really good random sample, S should be how related to sigma. Close. And in fact, I expect it to be equal to sigma. I just understand at the same time that it probably won't be equal to it. It'll be close. So this highest peak is when S equals sigma, which means the highest peak would be the degrees of freedom. If S equals sigma, these would cancel, right? So this highest peak for this problem would be, what was it, 39. And we just got a chi-square of 35.288, which is right here, right? We don't know what this means yet. We don't. I'm just trying to get you used to how this kind of looks when you try to figure out where things are on this picture. Okay, now. How much time do I got? I got very little time. Damn. Coming back to the chart real quick. I know I'm doing a lot of weird shit. So everybody got those values down here? No? Sorry. Did I do one that's even on here? Close enough. Damn it. Jeff. What you got? I don't know what's going on there, Alex. Hold up. Let me see. Put it up there again. I got to see yours. Oh, do it. I'm sorry. Put it closer. Put it up in your camera. I can't see. What happened? I see the problem. Sorry. That's 7.8. 7.8, right? It looks like you have 2.8. It's 7.8. That's just my bad writing. Do you understand what I'm saying? Not 2.8. I think you have 2.8. That's my fault, not your fault. Okay. All right. I'm sorry, Alex. Okay, good. So you're good. All right, let me see. This is really poor planning on my part. I'm sorry. This is not going to be perfect, but oh well, I'm not perfect. Degrees of freedom for us, if I would have thought far enough ahead, because when I started doing this, I wasn't thinking about doing what I'm about to do. And of course, they don't have 39 degree of freedom, do they? Ugh, Jeff. But, oh well. Do you see, look, what's right in the middle? Now, is everybody with me on this? Do you see why I'm looking here? Because that's the closest to my degrees of freedom for this problem we were just doing, right? You guys with me? Because what's that column? That first column is all about degrees of freedom. So I go down, 39 would be great, but Jeff is not very smart, so he didn't pick one that was on here, but let's all just get past that, because I have accepted it. Do you see how right up here, right in the middle of those two, if you look right in the middle of 29 and 51, you do get 40. Right? And it's not perfectly in the middle because this is not perfectly symmetric. Let me stop for a minute. So I'm just verifying that it looks like that highest peak. It makes sense that it would be the degrees of freedom. All right. What do we get? We got 30. What do we get? 35.288. Do you see how that's not very far above this? Right, so it's kind of like makes sense where it is on the picture based on where it is on the table. Okay, let me stop there for a minute because I'm not really sure how useful this is, but I just want to get a little bit deeper into what the table means related to what it looks like on the graph. All right, now. What you're really going to probably hate me for, it seems like every time I meet with you, I try to make sure that everybody hates me. I think I've got almost 100% hatred. So let me see if this pushes me over. We're not going to use this formula. All right. Right there, you guys probably, just by me saying that, you hate me. And I don't apparently care. That's a very good formula to at least look at because it does describe why, it makes sense what the shape looks like. What we're going to focus on is this. It's called goodness of fit. Good Lord, Jeff. Goodness of fit. And that is the actual official name. So what this is used for, does this sound useful? I have a population, and I want to see if a certain group in the population follows the expected distribution. Like if I look at a certain town and I say, do people's ages follow what I expect them to be, like the general distribution of ages? So then I can test to see, is one town statistically significantly younger or older or just different from the general population's ages? Let me just stop right there. So if, for example, let's see, let's say that I have, somebody gives me a die, right? Like from a pair of dice, a die. And they say, can you check to see if this die has been tampered with? And why would somebody tamper with a die? What could be a reason for somebody to tamper with a die? To win a bet. I love it. So they can win at craps. They can, yeah, shooting craps. There we go. Malachi's got it. To win something. Or maybe it's a D&D die. A D&D die? 20-sided die, and they wanted to come up 20 more often so they can get more damage on the monsters and stuff like that. I don't know if anybody ever plays D&D. All right. So that's the basic idea. So let's just say it's a normal non-D&D die, and I just want to wait to somebody, normal? What's normal? I'm a D&D. Oh, shut up. So what are the possible outcomes? And for some reason, I'm going to call them categories. What are the outcomes of rolling a die? Normal, 6-sided die. There we go. 1, 2, 3, 4, 5, 6. If it has not been tampered with, what do I expect to happen? So let me say this. Let's say we roll a die, roll it 60 times. Right? I'm going to roll this die 60 times to test it. What would I expect? How many of each of these would I expect to show up if it has not been tampered with? Not about 10, but 10, right? I know what you mean. We kind of build that in, which is good. You should have that built in. But expected doesn't mean it will happen, right? So we know it should be about 10, so I expect 10. And then I can see how far off from that expectation I am. Is everybody with me? Notice one thing about this test. This is the first time we've been able to do multiple values. We like with correlation, we can only handle 2 variables possibility. But here I got amounts of 1s, amounts of 2s, amounts of 3s, amounts of 4s. I've got all these different things. So I expect 10 of each. I know we expect close to 10, but why is it 10? Because 60 divided by 6 is 10. I expect on average there would be 10. So let's say this is what I observe. What you got, Jeff? Let's say I observe 7 1s, 8 2s, 12 3s, 13 4s. Let's see, what's that leaving me? 15, 15. Oh, okay. 30. Where am I at? That shouldn't be true, is it? Oh, that should be exactly what I need. 15 and you can do it just 25. It's 40. There you go, buddy. Good job, Jeff. 11 and 9. I think that should do it, right? 20, 30, 45, 60. Yes. Okay, thank God. Sorry, it took me a while. It's too early. Let me make this a little bit better. A little more lined up. Okay. Sorry with it so far. I mean, that's a possibility. Did I just roll a die? No. Do you have a problem with that? I don't care. Right. So if we did roll it and we saw these things, is that off from what we expect? Yes. But what do you mean no? Yeah, it is. We expected 10s. Now, I know what you're thinking, Alex. I expect close to 10. But the problem here is the exact problem we have with hypothesis tests. Right? Why did we have to do a whole hypothesis test? If I think the mean is more than 3 and my sample comes out to be 3.8, why don't I just stop there? Because it's more than 3. Why do we do all those freaking steps, Jeff? Huh? Because the idea of close is not easily determined on site, right? So we need some help with the idea of close. So I kind of agree that those do seem close to what I expect. So the whole point of this is, are they far enough away from what I expect to be evidence that something's happened? So in my gut, I would actually agree with Alex. I would kind of agree. Maybe these aren't far enough away, but let's see. So what's a good first step? What do you think, based on what I just said, what's a good first step for a next thing to do here? Yeah. In fact, let's do this. Let's go ahead. I can't remember if I do this. Observe minus, let me do it the same way I do it in this handout. I always forget which way. Yeah, okay, good. All right, I do this. I'm trying to minimize the number of columns we need. So yeah, you're right. It doesn't matter which way it ends up because I'm going to square. Why am I going to square them? The same reason we squared for standard deviation, right? Because some are going to come out negative, some are going to come out positive. That's not going to be good. So those two things make sense? The whole idea here is, how different are these? So of course I'm going to subtract. And then I square for kind of the same reason I squared when we did standard deviation. So what would I get here? 3 squared is 9. 2 squared is 4. 2 squared is 4. 3 squared is 9. 1 squared is 1. That's amazing, Jeff. You're so good at this. Now, I want this last thing to make sense, and then I might show you, shit, I didn't leave it open, damn it. I might try to find it again. I have like 10 minutes. Good. All right. Stay with me. This is so cool. Is that very big? Well, I have to relate it to the size of this. What if I expected, in some situation, I expected 10 billion, right? And I get 9 here. Is that a big difference? No, 9 out of 10 billion is not a big. So do you see how it makes sense? The next step should be relative to what I expected. Is that a huge deal? So the next step, the last column, thank God, for 2 reasons, so I don't have to make a big ass table and I'm about to run out of room, is to take what I just did and divide it by the expected. So I get a relative difference. Let me stop for a minute. Maybe not a full minute. I don't have that kind of time. So this makes complete sense. Squaring should make sense, just like the standard deviation. And then dividing by E might make not as much sense, but it still should make some sense. I got to say, relative to what I expected, is that difference important? Is that difference big, right? So if I do that, this is one reason why I made these 10s. 9 divided by 10 is 0.9. So all these just become 1 decimal place smaller. Is that cool? So that is the formula for chi-squared now. Chi-square, another formula, just like z-score had p hat minus p over square root of pq over n, and z-star had x bar minus mu over sigma x bar, right? But they all were z's. Here's another formula for chi-squared. Get out. Yeah, sure. Oh, I got to make this big. I always forget to do that. Rah. The sum of those. So just the sum of this column. So what do you get when you add those up? Looks like 2.8. Is that right? When you add those up? 1, 2.8, yeah. Okay, now watch. I got very little time left. All right, so everybody got that? This is all new, but it should feel familiar in a sense. In other senses, not at all. I understand. So everybody's got that. I'm going to pull up here. So here's the idea. Now watch. Here's what the chi-square looks like. What would it mean if I get a chi-square of 0 in this, for this problem? What would it mean if chi-square came out to be 0, if all these were zeros? That would mean that the expected and the observed were The same, exactly. Which would obviously not be evidence that they're different if they were exactly the same. So are these exactly the same? No, it's not 0. Is this difference big enough to be evidence that something has happened to this die? So let's see. So here on this picture, depends on exactly. I love it. So now we got to figure out how the hell to get that value. So here's the idea. 0 means not enough evidence, obviously. In fact, anything close to 0 would be not enough evidence. So I got to figure out, let's say that I want alpha to be 0.10. Right? So here's the major change with the goodness of fit test. The degrees of freedom formula isn't quite the same. Degrees of freedom formula is k minus 1. What's k, you might ask? K is because I think, no, actually, I don't remember the history, but just to make something up, here's the drunk history of k. Somebody didn't know how to spell categories, so they used k, right? These poor guys, they know enough, they didn't have too much math, not enough room for, spelling. So how many categories did we have again? Here's my thumb. What's going on with this thing? We had 6 categories, so my degrees of freedom is 5. So watch. Here we go. This is obviously the last thing we're doing because I'm almost out of time. But I want to show you. Come on, share the screen. Where are you? I got rid of you. Why did I get rid of you? There you are. Okay. So alpha is 0.10. So 0.10. This is that same column. This is if the degrees of freedom was 1. That's what we did earlier. 0.10. Degrees of freedom is 5. So what's the critical chi-square score? 9.236. That's actually kind of related to why they set this up the way they did, because this is a really quick way to find the alphas for a goodness of fit test. I can just focus here. So my chi-square critical score is 9.236. So right here, 9.236, get out of there. This is my rejection region, right? I'm not going to make you do a full hypothesis test for these. I'm not. You just cut to the chase. Did we make it far enough away? We got 2.8. Is that? No, we didn't make it far enough away. So have we found evidence that the die was tampered with? If the die had been tampered with, it's more likely that it would have shown up out here. The fact that it showed up there makes it more likely that it just had the random fluctuations I would expect with any die. It wasn't far enough away from what we expected. That's all. So your answer would be, we have not found evidence the die was tampered with. And that's all you have to say. I'm not going to make it as formal and official as a full hypothesis test, although I could if I felt like being a jackass. Right? And I'm working on a mullet, it looks like. Oh well. Party in the back. Crazy. We just did a lot. I know. So obviously, on Thursday we'll do at least a couple more examples of that. On let me see. Did I put that up here? Yeah. I don't know. Can you guys see that? Oh no, you can't see shit. All right, sorry. On the handout that's up on, so it's got this one side I said I was going to make a video on. On this side, it's got a fully worked out example using M&Ms. And then it's got a problem that we'll do next time, but you can take a look at it if you want to. Right? What about blood cholesterol level? Kind of makes sense. M&Ms, blood cholesterol level, they might affect each other. All right, but otherwise, I think that's enough for today. So again, just to remind you guys, quiz on Thursday on chapter 12, correlation, regression. and get into Canvas so you can make sure you understand how I've reorganized it a little bit. Okay. Anybody questions, need to hang out for a bit? Otherwise, if not, you could just leave. But if anybody needs to hang out, let me know. Alex is hopeful that today is the day he can see who's the last to leave, but I am the last to leave because once I leave, everybody's left. All right, I don't see anybody with questions, so I'm going to close things down. Thanks, Ree. You too. Take care, everybody. Stay safe. Be informed. Don't be stupid.